Alright, so for the ninth problem, so solve the following being for A, the elastic deflection curve, y-axis, the maximum deflection for B, and C, the location of maximum deflection, the maximum bending moments, and E, the maximum shear load. Okay, so basically you have to use the integration method. You should be able to have that in your mind ready and to be able to identify that right off the bat. So it's given the equation over here, so we just have to take the integration for 4 times. And yeah, to be able to get to yx, I think you should know the relationship here, right? Dy dx 4, you take the integration again, integration, which is d3 y dx 3, and then d2y dx 2, and then now it's 1 over ei dy dx, and then y, and then ei. Okay, so, and from here to here, I think you take the integral with the ei outside of the integral, just count it as a constant. Okay, so with this problem, yeah, you take the integral and you keep going. And also, because this is a y-axis symmetrical, and then there is a perfectly y-axis symmetrical distributed load, so you should be able to answer this question right off the bat. C of the location of maximum deflection, obviously, that's going to be at L/2, right? You should be able to answer C pretty easily, so that's going to y max occurs at L/2, right? Okay, so let's go on and solve the rest of the problem. So W x, right? It's going to equal negative W sine of pi over L x, right? It takes the integral. This is going to be sine, so then the next is cosine, right? So negative cosine. No, no, it'd just be positive cosine, right? Because it's sine, cosine, negative cosine, right? This goes to here. Okay, so it's going to be W, and then L over pi cosine of pi over L x, right? Should be able to execute this integration pretty easily from your pre-calc stuff. I mean, pre-calc stuff, calc 1 or calc 2, right? If you're having trouble solving this, then yeah, that's this video is not going to help you too much in terms of mathematically. Moving on. So this is going to be shear, and then this is going to be moment, right? You take the integration again. So this is, what did I do? I take the integration of this, and I take the integration of this. So now this is going to be, so cosine is going to move on to sine. So this is W over pi square, and sine of pi over L x plus C1x plus C2, right? And then now is where things get a little interesting, which this is the rotation, right? There's a different way to write it, like there's this, you know, or there is this kind of formality, but yeah, so this will be the 1 over ei, okay? Take the integration, so this is going to be, so it's going to be this, right? Moving on, so negative W L over pi, this is to the power of 3 cosine pi over Lx plus C1 x to the power of 2 over 2 plus C2 x plus C3. Okay, you do that again, and finally we are here with the yx, right? And ei this. Okay. So yeah, negative cosine is going to be negative sine, so W L over pi to the power of 4 sine of pi over Lx plus C1 x to the power of 3 over 6, right, plus C2 x to the power of 2 over 2 plus C3x plus C4. Okay. Now we have all these constants, right? So for question A, the elastic deflection curve yx. So we're basically halfway there. We got this. Now we just have to figure out what C1, C2, C3, and C4 is. So now, and then also we have some boundary conditions, right? So we know that C0, it's going to be equal to 0, which is also the deflection at when L equal to 0, right? So the deflection of angles at 0 is 0, right? Otherwise, there's going to be a discontinuity or bridge or whatever. This connection will break. As well as displacement, right? It cannot have a displacement. So the deflection will look something like this, right? I know you say, oh, what about the angle here? But at this very instant moment you zoom out, right? It's actually, if this is the wall, it's going to move up. And then at this very instantaneous little section, this is actually vertical, right? This is perpendicular to the wall, so it must be 0. Yeah, 0 angle. So also there's no displacement, obviously, right? If there's displacement, then this is, is broken. So as well as, well, at 0 is 0, so at L, right, on the other side of the wall will also be 0. Okay, so now we have 4, what do you call this? 4 boundary conditions, and we have 4 knowns. Usually, it's an indication of this problem is solvable. So let's start plugging a number into this part, right? This equation over here. So I don't know. Let's move down a little bit. Okay. So 1 over EI of theta x equal to 0, right? So EI will also be canceled out. We don't have to consider it because if we're setting it equal to 0, 0 times EI equals 0. And then, so yeah, you plug a 0 in. Cosine of 0 equals 1. Yes, that's correct. Cosine of 0 equals 1, so that would be negative this 3. Cosine of 0, that's going to equal to 1, right? Plus 0 plus 0 plus C3 equal to 0, right? So C3 obviously will equals to W over times L over pi to the power of 3, right? So now we have C3 solved. And let's write this in a different color up here for, clarity, right? C3 equals this, L over pi to the power of 3. Okay, perfect. Now, let's move on to, let's see. Oh yeah, so we plugged in one condition. Let's plug into the other one. Change back. So this is this boundary condition, right? Now let's plug in this boundary condition. L equals 1 over EI pi of L, right? Yeah. So this is going to be negative, right? Because if you plug L in, then L and L cancels out. So cosine of pi, that's going to give you negative 1. So this is going to be W over L over pi to the power of 3. Negative 1 cancel with a negative sign in front of it, plus C1L to the power of 2, right, over 2, plus C2L plus, so C3 is W over pi over L over pi to the power of 3. So now we can figure this out of, you can say, okay, C1 L over 2 times L to the power of 2 over L plus C2 L gives you negative 2W L over pi to the power of 3. So now it's 2 unknowns in one equation. That's not enough, but don't panic. Okay, we have 2 more conditions that hasn't been applied yet. And sorry, these 2 conditions, right, haven't been applied yet. So let's move on to this equation over here, right? So y of 0 that's going to be, let's see, y of 0 equals 0 equals, okay, so let's see. If sine of 0, that's 0, right? Sine of 0 equals 0. This is 0, 0, 0. So C4 equals 0, right? So we can write it up here. C4 equals 0. Okay. And now let's apply the other condition, right? Which is the y of L. Let's just apply it over here. Y, no, for formality. Okay, y of L going to this. This is going to be y of L equals, let's see, let's move, zoom out a little bit, yeah, okay. So plug into L. This is going to be sine of pi, so sine of pi is also 0, so this cancels out, this will become 0 again. It's perfect, we want zeros, right? So now it becomes C1 x to the power of 3, C1 L to the power of 3 over 6 plus C2 L to the power of 2 over 2 plus C3 L and plus C4, which is 0, so we don't have to write that. And C3, we also figured that out over the top, right? Which is, this is going to be W L over pi to the power of 3 times L. Does the whole thing equal to 0. Perfect. Now we can write, so let's say C1 L to the 3 over 6 plus C2 L to the power of 2 over 2 equals negative W pi L over pi to the power of 3 times L. Right, now we can get rid of an L on both sides, right? So now it's C1. So now it's, let's see. Now it would be C1 L to the power of 2 over 6 plus C2 L to the power to the L to the 1 over 2 equals negative W over pi to the power of 3. Okay, now these two, the units is going to work out. Perfect. We want that. And we can just write one in terms of the other and substitute. Or you can use 2x2 matrix and find 2x3 matrix, use determinant to find it. Excuse me. Or on your TI-84, I think there's a polynomial solver. But I don't think you can substitute elements or like x and y's, but anyway, we're gonna do the substitution method. So we're gonna times let's see, so C1, this is gonna be C1 L over 2 plus 2CL over 2 C2L equals negative 4W L over pi to the power of 3, and this thing is gonna become C1 L to the 2 times 3 C2L equals negative 6W L over pi to the power of 3. Perfect. And now we just substitute one into the other. So this is gonna, so there's I think two ways to go about it. I think there's the typical, like you said, C1, right, L2 equals the rest of this equation and plug it into this one, or you can use those two equations to one minus the other. So let's say this equation, the bottom equation minus the top equation, so this minus that cancels out this term minus this term, this is going to give us C2RL, and this term minus this term is going to give us negative 2 W L over pi to the power of 3 divided by L. C2 is negative 2 W L to the power of 2 over pi to the power of 3. Voila. Right, now we have figured it out. No, not yet. C2 is going to be negative W L to the power of 2 pi to the power of 3 and W, right? Perfect. Okay, so now we have C2. We just need to plug in and find what C1 is. And if you're tried it, and to figure this out, you already know that C1 is 0, right? Because you plug this number back into here, right? So that's 4, and you plus 4 both sides. That's going to give us a 0, so C1 equal to 0. Okay. Right. And you can also plug into this one, right? Which is 6 plus 6. Yeah, 0. Cancels out. Okay. Now we have all the coefficients. Let's plug it in back to the yx equation to find out what the maximum deflection is. Or, well, theoretically, we're still figuring out what A is, right? It's taking for freaking ever. So now we can officially say, oh, A, right? Let's use a different color so you guys can check it out easily. Okay, there we go. So A, we're gonna plug in all the numbers back. So EI x, yx equals W L over pi to the power 4 sine of pi over Lx, right? Plug times C1 is 0, so that's perfect. C2, on the other hand, is a number. So it's negative 2. Yeah, negative 2. Oh, okay, I gotta rephrase it. So W, yeah, L over L to the power 2 pi over power 2 times x squared, and then over 2, right? So this cancels out. And I'm plugging in C3, which we already calculated to be C3. C3, what is C3? C3 is WL pi to the power of 3, and then times x, right? And C4 is also 0, so we neglect that. Okay, perfect. So we plugged everything in, and now we already figured out what C is, right? So the location of maximum deflection. So we can just say, okay, well, we represent this equation in a unit in a function of x. So let's plug it in. So y of x, so L over 2, right? It occurs at L over 2, as we says over here, because it's symmetrical. This would be L pi over this. So L over 2, but before we go on, so L over 2, right? Cancel. So what is pi over? So what is sine of pi over 2? 1, right? So that's going to give us 1. Perfect. We'll just leave it as the way it is. And minus pi over pi to the 2 times L2 over 4, right? And let's keep going, plus W pi L over pi to the power of 3 times L to the power of 3 over 2, which is 8, right? Over 8. Okay, and then I'm pretty sure this is the answer. For B, C already calculated, that's perfect. And then let's try to figure out D. I'm going to start writing over here because it's better to keep everything in one page. And maximum shear. Okay, so I would suggest to do E first because once yeah, I would suggest, it doesn't matter, I guess. It doesn't really matter. Let's do D, actually. Follow the steps, right? So we have this. So how do we find the maximum of something out of the equation? We take the derivative and we set it to 0, right? Optimization. So in this case, we're gonna set Vx. Oh shoot, sorry. This, remember, all this, you have to time EI, right? Okay, so moving on. This equation, we're going to set it to 0. We're going to figure out what x is, right? So this is going to be W L over pi cosine of pi over L times x plus C1. C1 is 0, so cancel that. Okay, so either this is 0, which is not possible, right? Or you set this equal to 0. So how do you get cosine equal to 0? You get x is either going to equal to 0, no, equal to pi over 2, or 3 pi over 2, right? So how do you, so now, so cosine of pi over 2 x is going to have to equal to pi over 2. Pi over L, sorry. So how do you make this section equal to this? What does x have to be equal to? It has to be equal to L over 2, right? L over 2. Or it's, so when you set it to 3, so x have to be 3L over 2. Now this is impossible. This is over the limit, right? Sometimes you have to interpret it of math in reality. So this is impossible, right? So we're going to keep this this number, so we're going to plug it back into the mx L over 2, right, equals m max, right? It's going to give you w L over pi 2, and sine of, so this is L over 2, cross it, sine of pi over 2 equals 1, perfect, plus C1. What is C1? C1 is 0, C2 is negative minus pi, minus 2 W L over 2 over pi over 3. Okay? And this is M. This is M. And then same thing, right? We take the derivative. So for E, same procedure, right? We have to use V of x. So, sorry, go to W and then x equal to 0. Set it to, I don't freaking know. Wait, yeah, it's negative m, W sine of pi over L x, right? So now you ask yourself, okay, well, how do I make sine of pi over L x equal to 0? Well, when sine equals to 0, it's either going to equal to 0 or pi, right? So x has to be equal to L, or x has to be equal to 0, right? Pretty straightforward. It's so the left and right. In this case, we're going to plug that in. So you can just do 1, right? So let's just say do 0. Cosine of 0 is 1. Cosine of 0 is 1, so it's W L over pi and times 1, and C1 is 0, okay? And this is the other answer. Okay, well, this is the end of this problem. It took us about, 20 some minutes, minus the part where I was having a brain fart, or, I'm just explaining stuff. It took, about 18 to 20 minutes. It depends whether you're slow on the mathematics. But, if your professor put this on the exam, well, you are either in a very, very special course in MIT, in an exam that's 1 hour and 15 minutes, right? And this is the 9th question out of 12. Then, yeah, you must be crazily smart. So, but yeah, hopefully you're able to understand, and I hope this whole procedure, this whole journey that I've demonstrated and presented to you helped your understanding of sort of like the general, process of solving this kind of problem. This is already a simplified version, right? This can be a lot harder. Like the equation, like the integration here, it can be a lot harder, right? And the C1 and C2 gives you 0. In real life situations, usually it's a lot harder, but we have machines. So, but yeah. Okay, well, hopefully this was helpful. So yeah, good luck in your studies, good luck in your reviews, and I'll see you in my next videos.